there is a direct correspondence between your ideals being prime and the corresponding varieties being reducible. Let me show you. So, of course, as usual, we're working over an algebraically closed field. Which you might as well as think of as C. And we look at variety X, and inside this variety X at variety Y. And now we want to talk about prime ideals and this subvariety Y being reducible. So first of all, let me remind you, because we have talked about this in a previous video. Let me remind you what reducible means. So Y is called reducible if it is the case that you can express Y as a union of two non-empty closed proper subsets. So y1, y2 are both unequal to the empty set, and also unequal to y. So this is the notion of reducibility. And what we're going to see here is that prime ideals correspond to irreducible subvarieties. So let's say we have the ideal of y, I of y, and an element of this I of y is this product here, f1, f2, of two polynomials, f1 and f2. So this is an element in I of y. In other words, this product of polynomials vanishes on the subvariety I. So this is what we assume. But f1 is not an element of I of y, and neither is f2. So the product of f1 and f2 is an I of y, vanishes on y, but taken alone, f1 and f2 do not vanish on I of y. So what this means is that the ideal of I of y is not prime, right? This is precisely what we are assuming here. The ideal of y is not prime. Then what this implies is that we can express y as a union of the vanishing set of f1 and the vanishing set of f2. And well, this is precisely this condition here for reducibility. So y is reducible if we assume that I of y is not prime. Then we see that y has to be reducible. And let's try to look the other way around. So let y be reducible. So y is by definition a union of two non-empty proper closed subsets y1, y2. Then these subsets y1 and y2 being non-empty closed means that there exist f1 in I of y1 and f2 in I of y2 such that f1 is not in I of y, so it does vanish on y1, but it does not vanish on all of y. And similarly for so this is of course I meant to write not an element of I of y, sorry. So f2 is not an element of I of y. And the product f1 times f2, well, the vanishing set of this product f1 f2 is the union of the vanishing sets of f1 and f2. In other words, it is y1 union y2, which is nothing but y. So we see that this product f1 f2 is in I of y, while these polynomials f1 and f2 are not in I of y, and this means that I of y is not prime. So if you look now at both of these statements we have proved, we have looked at this one here and this one, you see that there is this correspondence between prime ideals on the commutative algebra side, and these correspond to irreducible varieties. Right? Or in other words, non-prime ideals correspond to reducible varieties. This is more precisely how we have looked at things here.